Hey AP Chemistry, so this is a video on questions 8, 9, and 10 of problem set number 3 in our equilibrium unit. This was asked by Yazan, and I'm really glad that I'm making a video on these 3 questions because I wanted to make sure that you had more practice and more understanding of the different types of calculations that are required for equilibrium. So let's look at question number 8. It says, consider the equilibrium, and I have this reaction. I fixed a typo. It should say 3 moles of each N2O and O2. This is not in your problem set. I messaged in the remind. Make sure it says 3 moles of each N2O and O2 are introduced into a 1 liter evacuated flask. When the system comes to equilibrium, 0.0101 mole of NO gas has formed. Determine the equilibrium concentrations of each substance. Calculate the Kc. Now, this is a question in which you could use an ICE table, kind of like a BCA table, where we have an equilibrium concentration, right? So this is a type of question where we have an equilibrium concentration. And from there, I can solve for my Kc. So I'm going to plug in these numbers, and then just to make sure you make a note, brackets equal molarity and concentration, and molarity is moles over liters. Now, this question gave me 3 moles and a volume. Moles over liter gives me my concentration. Now, of course, you could use moles in this table, but then you have to be careful to make sure you put it into or have it in molarity later. Since everything's 1 liter, if I have 1 liter, my moles equals my molarity. That's just like a note to make things easier because it's dividing by 1, but I'm still going to see moles equals molarity if that's 1. I'm still going to show it just in case I don't always have 1 liter. Initially, I had 3 moles of each of them in 1 liter. That's equal to 3 molar. So I have 3 molar N2O and 3 molar O2. No initial NO. This is before the reaction. By the way, I have this up here. This is the reaction. Sometimes these are called Rice tables for reaction initial change equilibrium. Plus, and then equilibrium. Initially, I have no product. And then it says later on, the system comes to equilibrium, 0.001 mole of NO has formed. So I'll also convert that to liter molarity just in case. Moles divided by the same 1 liter. It's an evacuated flask. It's not, the volume is not going to change. Everything's happening in the flask. So 0.001 molar. And that's going to be down here, 0.001 molar. Okay, now this is exactly like we did our ICE tables in the beginning of our notes. If you find our notes from Unit 7 Important Information Part 2, where we do a bunch of ICE tables, I could use my given equilibrium concentration and solve for everything that's missing. So in order for me to have gotten 0.01 molar, I must have added 0.01 molar in the change section. And now I could use stoichiometry and dimensional analysis to figure out how much O2 and how much N2O I must have used. Well, this is a 4-to-1 ratio. So if I want, I could do 0.001 molar times 1 molar of O2 for every 4 molar of NO. It's a 1-to-4 ratio. Basically, I'm going to be dividing by 4. It's going to be a really small number. I did this on purpose for question 9. Notice how I know I'm going to eventually get a very small Kc because I don't have that much product. I'm probably going to have a lot of reactant. So if I take this number and divide by 4, I'll figure out how much O2. I'm going to do it on my calculator. 0.001 divided by 4. 2.5 times 10 to the minus 4th. I'll just put the decimal. It'll be 0.000123425 molar. Right? This is 2.5 times 10 to the minus 4th. 1, 2, 3, 2, 5. 2.5 times 10 to the minus 4th. Right? And so eventually, if I take these 2 columns and put them together, I'll see how much is it at equilibrium. I'll do the same thing over here. This is a 4-to-2 ratio. So I'm going to have half as much of this used up from the N2O. So whatever number I get here, this is a 2-to-4 ratio. This number must have been multiplied by 2 to get this. If I'm going this way, if you can't see it, you could use dimensional analysis. 0.001 molar of NO times 2 molar of N2O for every 4 molar of NO. This is a 2-to-4 or 1-to-2 ratio. Basically, I'm going to be dividing by half, 0.001. If you can't see it, I'll do the dimensional analysis, times 2 divided by 4. And I get 5 times 10 to the minus 4th, which is going to be 0.0005 molar. And that's going to be minus. Okay? Again, how did I get these numbers? Stoichiometry. This is a 4-to-1 and a 4-to-2 ratio. We do minus because reactants are used up. And we do plus because products are made. I add the initial and change together. So 3 minus 0.005, get a big number. 3 minus 0.0005, I get 2.99995. I'm going to put all of those digits in there because I need them. 2.9995 molar remained. And then for this one, it's going to be 7.5. But I'll do 3 minus 0.00025, and I got 2.99975. I'm going to put that there. 2.99975 molar. And that's how much product is made. I have my equilibrium concentrations now. I was only able to do this because I had an equilibrium concentration, so I do stoichiometry with this. And so now, if I want to calculate Kc, there's not that much space, but I plug in products over reactants. NO to the 4th over N2O squared times O2 raised to the 1st. I use the stoichiometric coefficients for this. And now I just plug and chug the numbers. I'm going to put the numbers here, but then I'm going to put the answer up here. So NO to the 4th is going to be 0.001 to the 4th over 2.9995 squared times 2.99975 not squared. So I'm just plugging in these numbers and putting them into the Kc. I'm sorry this is getting squished, but you write the Kc expression and I have all the numbers that go into the Kc expression. If I do this math correctly, I'm going to be doing 0.001 raised to the 4th, very small number, divided by, I'm going to have 2.9995 squared times 2.99975. And I get a very small number. Kc is equal to 3.7, I'm going to say 1 times 10 to the minus 14th. Oh, 14th, not 4. 14th. Okay, so the answer to question number 8 for our problem set is going to be, these are my equilibrium concentrations. Notice I have a very, very, very small concentration of my product and a very large concentration of my reactants, and my Kc is really small. This means this is reactant favored, and essentially I mostly have my products. That's going to be very important for question 9. In my next video, I'm going to use this information and this Kc to solve for question number 9.